Hi, everybody. Hope that you're all doing well and that you're safe. And we're going to go ahead and move on today. We've taken care of Chapter 9, Section 1 on finding roots. And there's one thing I just kind of want to pull away from that section before we move into 9.2. I spoke in the last video that one of the key elements that we're going to be involved with in Chapter 9 is taking a look at very specific rules that we need to make sure that we follow when we are either finding roots, simplifying roots, operating with roots. And that first rule, I'm just going to show it to you right now as a review. That first rule from 9.1 was, if a radical expression represents a rational number, we write the rational number in place of the radical expression. Now, those three radicals that you see at the very bottom of this sheet of paper, all three of them represent rational numbers, because all three of them have radicands that are perfect nth powers. The one in the middle is a perfect square, 25. The one to the left is a perfect cube, -8. And the one on the right is a perfect fourth power, 16. And all three of those on the bottom, when evaluated, give us a rational number. So that was rule number 1. Now we're moving into 9.2. And in 9.2, we're going to be looking at the first two operations of radicals: multiplying radicals and dividing with radicals. We're going to be looking at multiplication of radicals first. And there is a formula that we're going to be following when we are dealing with the multiplication of radicals. So we're going to turn the attention now to the board, and we're going to spotlight what 9.2 is going to direct us to do. We're going to multiply and divide radicals. And we are going to use the multiplication rule and the division rule to also simplify radicals. Now, like I just mentioned moments ago, we're going to start with multiplying radicals first. And there is a rule, a property, that we have to follow when we are working with multiplication of radicals. It's called the product rule of radicals. Product not only indicates a possible answer to a multiplication problem, but it also just simply indicates multiplication. So the product rule of radicals has everything to do with multiplication. And here's the rule, and we will prove it so that you see that it'll be a true statement. Rule: if A and B are real numbers where roots exist, here's the rule. Here's the product rule of radicals. The nth root of A multiplied by the nth root of B is equal to the nth root of A times B. Now, one thing on the surface that's going to be key to this product rule of radicals: we can only multiply radicals together if the indices, the plural of index, if the indices are the same. So if the index on the radical of A is n, then the index for the radical of B is going to have to be that same n index. Now we're going to prove it. Let's assume that n, the index for our proof, is going to be square root. So in other words, we don't see the little index of 2, but there's actually a 2 there, a 2 there, and a 2 over there on the right-hand side. Our value of A is 9, and our value of B is 4. I wanted to pick perfect squares to show the proof, but we could pick any non-negative number for A and B, and it would still prove out to be true. Now here's what the rule says. The radical of 9 multiplied by the radical of 4 is equal to the radical of 9 times 4. I elected not to go with a parenthesis inside there, so don't make the mistake on this video thinking that's a decimal point. It's not. Now let's come down back to the left-hand side, and let's simplify this radical of 9. You see, as I'm pointing to it right now, this is rule number 1. That little radical represents a rational number of 3. I'm bringing it down. Bring down the times sign. The radical of 4 also represents a rational number. The rational number is 2. I bring down the 2. And that's going to be equal to the radical of their product. I'm multiplying the 9 and the 4 together to generate that 36. Let's return to the left-hand side. 3 times 2 is 6. Bring down the equal sign. The radical of 36 represents the rational number 6. We bring the 6 down. 6 equals 6. It checks. So the product rule of radicals checks. It lets us know when we multiply two radicals together that have the same index, it will always equal the nth root of their product. The nth root of their product. This rule right here, this property, is now going to be used to do two specific things pertaining to multiplication. The first item that this property will do for us, it will help us to multiply radicals together. And the second thing that this property will allow us to do is to simplify a radical or simplify radicals that also involve multiplication. So now we're going to go over here on this side and we're going to do the first objective of the product rule of radicals. I just rewrote that property rule right up here again. I'm not going to repeat it. I've just written it right back up there again. To multiply radicals, that is going to lead us to rule number 2. Now, folks, remember at the very beginning of this video, I replayed rule number 1 from 9.1. Now in 9.2, we're going to look at quite a few other rules. And the first of those is rule number 2. And it is the rule that will enable us to multiply radicals together. And here's rule 2. You'll want to know it. If a radical expression represents a product of radicals, multiply the radicals to get a single radical. That is exactly what we did on this product rule. Why did I box this left-hand side off in red? Because of what Rule 2 tells us that we're going to follow. Now Let me say that rule again, and I'll kind of point to this. If a radical expression represents a product of radicals, we multiply them together. We take the radicand of the first one, multiply it to the radicand of the second one, and write that product as a single radical, the nth root of a times b. We're going to come down here on problems 1, 2, and 3, and we're going to follow rule number 2. Let me state that rule as I kind of point to number 1. I want to make sure that this digests well. If a radical expression represents a product of radicals, we multiply the two radicals together to get a single radical. So what do you simply do? I'll kind of show all the steps on number 1. You make one radical sign to begin off, and we're going to take radicand number 1, and we're going to multiply it by radicand number 2, house it underneath 1, then literally multiply, and your answer is the radical of 35. A very, very basic rule. But you have to be alerted to that rule. Whenever you see a situation to where 2 or more radicals are being multiplied together, you multiply their radicands together and write that product below one single radical. Number 2, I'm going to shortcut now, like you can do. The radical of 11x multiplied by the radical of 10y. You don't leave it that way. We need to multiply them together. You make one radical, and you multiply the two radicands together, beginning with the coefficients first. 11 times 10, 110. X times y, xy, done. We've written the product as a single radical. Number 3. Let me just kind of erase this little section right here. Number 3. The cubed root of 4 multiplied by the cubed root of 9 multiplied by the cubed root of 5x. Notice that the indices must be the same, and they are the same. So when we multiply those two radical expressions together, make sure that you include that index. It's no longer square root. Get that 3 in there. Let's start with the constant factors. 4 times 9 is 36. 36 times 5, 180. And then just bring over the x. And it has been multiplied, and it's done. That is the first rule of 9.2 under the caption of multiplying radicals. If a radical expression represents a product of radicals, multiply the radicals together to get a single radical. And that we did on those first 3. Okay, now we're going to move into the second objective that the product rule of radicals can generate for us. In the first function of that product rule, we use that product rule to multiply radicals together. Now we're going to use that same product rule of radicals, but we're going to put the emphasis on the other side of that property. And when we put the emphasis on that other side, it's going to allow us to do the second function and that's simplifying radicals. Now, before we take a look at this property again and move into rule number 3, that's going to help us simplify radicals using this product rule, I want to mention this before we actually go to the rule and go to the examples. The radicals that you are going to be seeing up here that we're going to simplify, all of these radicals are going to represent irrational numbers. That's going to mean the radicands are not going to be perfect nth powers. They're not going to be perfect nth numbers. They're going to be non-perfect nth numbers. They're going to represent irrational numbers. And one other thing I want to mention before going into this. We are not going to be using the calculator at all when we simplify these radicals. We're simply going to make use of the product rule of radicals to get our specific answers. And one thing you're going to notice when you look at each one of the answers to the examples that we're going to do, each one of the answers are going to have radicals in them. But they're going to be simplified as far down as we can go, because we're not going to be using a calculator. We're going to be doing what's referred to as writing our answers in simplified radical form. So let's move to letter B of multiplying radicals. Letter A was multiplying radicals. Letter B, we're going to simplify radicals using the product rule. And notice I wrote the product rule up here again. But notice that I switched the sides of the equation and I wrote the nth root of the product of A and B is equal to the nth root of A multiplied by the nth root of B. When we use the product rule of radicals to simplify, this is going to be the key structure that we're going to have to get to start off with. We're going to have to form this side first. And once we get this side, then we'll break it down into the other side. And you will see as we go through and do it. Now, before we even do any of the examples, we need to speak to rule number 3. I'm not going to repeat rules 1 and 2 now. You have them. Here's rule 3. This rule has everything to do with simplifying radicals using the product rule. A radical expression is simplified when the radicand contains no perfect nth factors other than 1. A radical expression is simplified when the radicand contains no perfect nth factors other than 1. Why did I say perfect nth factors and not perfect square factors? Because not all of the radicals that we're going to be looking at are going to be dealing with square root. We're going to be looking at cubed root. We might be looking at a fourth root. We could be looking at any kind of a root. Now here's what we are talking about in terms of simplifying. Back over here on number 1, we're going to begin it in this way. Take a look at that problem on number 1. They want us to simplify the radical of 63. We're dealing with square root because there's no index number in there. So, rule number 3 says, a radical expression is simplified when the radicand contains no perfect square factors other than 1. Here's what we need to do with this 63 first. We need to determine, we need to identify two factors, two numbers that multiply together and equal 63. But people, not just any two factors. One of those factors must be a perfect square. The other factor will just be an ordinary irrational factor. Our first factor, A, must be the largest perfect nth factor, or in this case, the largest perfect square factor that 63 has. The B factor, the B radicand, will be the other factor that multiplied together with this A factor gives us the 63. Now that other factor is going to be an irrational factor. Now, as we move into this area from time to time, prime factorization is going to be a key item to do. And I'm even going to show it on number 1. Even though some of you out there that are viewing this video right now, you very likely already know what the largest perfect square factor that 63 has. But since I'm talking to a sizable group, I want to make sure that there isn't any confusion at all. So we're going to determine that largest perfect square factor that 63 would have by making use of prime factorization that we have already done. So I'm going to kind of squeeze it right here. It won't take long. So just kind of bear with me, those that already know. Jot down that 63. We can't divide it by 2 because it's not even. So let's go to the prime factor of 3. 6 plus 3 is 9. 3 will work. 3 will divide into 63 21 times. Make another upside down because we can divide it by 3 again. 3 divides into 21 7 times. We're done with our process because the remaining number down here is prime. Notice there's 2 of a kind for the 3's. We have a 3 squared right here. And 3 squared, because its exponent is 2, is a perfect square. And 3 squared happens to be the largest perfect square factor that 63 would have. Because all of the other remaining factors that we see here, we don't see any more 2 of a kind. We see a little loner down here of 7. So now we can identify our 2 factors. And for this particular problem, I'm not going to use an exponent. I could, and I will later on, but I'm not going to here. This first pair of 3's generates a 3 squared. And if we multiply those together, we get 9. 9 is our A, because 9 is the largest perfect square factor that 63 has. It's the only one that it has. So I'm going to just start off on this one. I'm going to put a 9 right there, and I'm going to put a little dot. I'm actually just going to follow this. And my factor of B is going to be the leftover irrational factor of 7. And now we're going to come over here on this right-hand side, and I'm going to let the radical of A be the radical of 9 times the radical of 7. And then, folks, we come down with an equal. And we follow rule number 1 when working with radicals, and we write the rational root for him, which is 3. And we simply are going to multiply that by the leftover irrational 7, and there is the simplified radical form answer that we get. Now, before we leave number 1, I just want to share something. If you took your calculator, you turned it on, and you punched in 63, and you hit the radical button, Kristen will show it right up here. That answer in green will be the numbers that you will see on that screen. 7.937253 ... That would be the approximated answer for the square root of 63. If you then cleared that on your calculator and then went down and did another item on your calculator, go to our answer right here. If you punched in 7 on your calculator and hit the radical button and let all those answers stay up there, and then hit the times button and times it by 3, because that's what this means, your answer that you'll get will be the same as that green one up there. This is another form of the approximated square root of 63. And that is the simplified radical form answer that we're going to use. Okay? All right. I'm going to kind of erase this stuff right here so I have plenty of room to do the other ones that we're going to be taking a look at. Okay. We're going to move into problem number 2. And before we do number 2, I just want to relate to you how I'm going to cut out maybe one of the little steps. Beginning with number 2, when we identify our factor A and our factor B for the given radicand that we're looking at, I'm going to avoid filling them in on the left-hand side. We're going to immediately go to the right-hand side. And as you can see right here, I've got number 2 ready to go. Here's our problem. -3 multiplied by the radical of 150. So I brought the -3 down, and I'm getting my A radical ready and my B radical ready, and I'm going right over here to 150. Now keep in mind we're dealing with square root, so we're interested in the largest perfect square factor that 150 would have. So let's bust it down and we'll be able to see what that is. It's even. We'll do it by 2. 2 will divide into 150 75 times. Make another upside down. No more 2 because he's odd. Let's go to 3 and test it. 7 plus 5 is 12. 3 goes into 12, 3 goes into 75. Put a 3, divide it, 25. Make another one. No more 3. The next prime is 5, and there it is. 5 there, and 5 there. If you look at these series of 4 prime factors right here, you want to look for any 2 of a kind, because any 2 of a kind represent a square. Those 2 little puppies right there represent the square. So I'm just going to multiply those together. 25. That is our A radicand. We don't have 2 of a kind of the 3. And we don't have 2 of a kind of the 2. So we multiply those 2 together, and that little product of 6 gives us our B radicand. Now, come down, let's simplify. Down. Put a times sign. Pull him out. He represents a rational. Times the radical of 6. Multiply those 2 together. -15 root 6. Simplified radical form. Done. Yes, I'm a proponent of this. You bet I am. Takes all the time away, saves time. The radical of 57. Let's see what develops when we prime factor. We can't do a 2. We go to 3. 5 plus 7 is 12. 3 works. 3 will go into 57 19 times. 19 is prime, just like 3 is, because you can't bust down 19 any further. You don't have 2 of a kind of the 3. You don't have 2 of a kind of the 19. The radical of 57 is already in simplified radical form. Can't bust it down. Can't do this. It doesn't contain any perfect square factors. So you would just leave your answer as the radical of 57 and it would be done. All right, let's go to number 4. And let's take a look at something that is different. We'll stay with square root, and we have this. What if the radicand is a variable expression? Well, remember, a variable expression in which the exponent is even, assuming that the index is square root, if the exponent is even, then it represents a perfect square. That exponent is not even, so it doesn't represent a perfect square. It represents an irrational number, just like the prior 3 problems that we did. So how do we treat something like m to the third? Well, one saving grace that we won't have to worry about, we will not have to worry about prime factorization for this one, because the coefficient of m to the third is 1, and it's not, prime factorization is not needed. Here's our rule. Let's bring down 2 radicals. One of them will be our radical of A, the second one will be our radical of B. How do we pull out the largest perfect square factor that m to the third has? Folks, remember these words. Take your odd numbered exponent and simply decrease it by 1. Take 1 away from 3. You will always take 1 away from, in this case, the odd numbered exponent. If you take 1 away from 3, you'll have an m to the second. The largest perfect square factor that is within m to the third is m to the second. Because remember, m to the third is this. You take any 2 of a kind. He's left over. That's the largest perfect square factor that m to the third has. What's the quick way? Decrease the 3 by 1. You'll be left with an m squared. M squared is the rational factor. And the leftover m is the irrational factor. Now, you don't have to worry again about absolute value. Get that out of your mind. Let's write down the square root of m squared. Bring down the m. You can take that exponent and divide it by the index. 2 divided by 2 is 1, or simply m multiplied by the radical of m, and he is done. Now, we'll continue to see this item as we move on. Let's go to 5. And number 5, let's treat this guy again, just to make sure that there's not a doubt. Folks, it's always important to look at your index. Don't start seeking things from that radicand until you look at that index. It's square root. So we're going to bring down our 2 radical signs. There's going to be our largest perfect square factor of g to the 17th, and that's going to be the irrational. Simply do this. Go to the odd exponent of 17 and decrease that by 1. You'll have g to the 16th. The largest perfect square factor within g to the 17th is g to the 16th. And the leftover one will be g. Now you can test it. G to the 16th times g to the 1. Add those exponents, g to the 17th. Now he's a perfect square. Bring down the g. Take your exponent of 16 and divide it by the exponent, divide it by the index of 2. 16 divided by 2, or merely cut 16 in half. You'll have g to the 8th multiplied by the radical of g. Done. Pretty basic. The variables are easy to work with. You don't have to spend a whole lot of time seeking out the largest perfect nth factor that it has. And now let's go to this guy, number 6. Negative 6ab multiplied by the radical of 56 a cubed b to the 10th. My eyes see this. Square root. So I'm interested in the largest perfect square factor that radicand would have. I don't want to keep scratching my head about 56. I don't want to try to figure out what it's going to be, and then if I see a number, you're asking, well, is it the best? You'll get the best if you bust it up. Now there's a 2, and it'll go 28. There's another 2. That'll give you 14. You have a third 2, and that'll get it down to 7. He's prime, you're done. You pick every 2 of a kind. We have 2 2s right here. That little guy would need another 2 for us to be able to use him. So we're not going to be using him, but we are going to use those. That will generate the largest perfect square factor. Their product will generate the irrational. So let's get this thing ready. Down. Make 2 of them. Here's going to be our rational house. Here's our 2 of a kind. If you want to put 2 squared there, you may. I'm going to put 4. That's going to take care of that. The 2 times 7, you see, you don't have another 2. If you had another 2, that would also go in here. We don't. 2 times 7 is 14. That goes in the irrational. Now let's go to our letters. We've dealt with 56 now. A to the 3rd. 3 is odd. Decrease that 3 by 1. In the rational house, you'll have an a squared. In the irrational house, you'll have an a. B to the 10th. He is even. He's even. So you don't have to subtract anything. You put that entire b to the 10th in the rational. And now let's carefully do this. Bring this down. Times the radical of 4, 2. The radical of a squared, a. The radical of b to the 10th, divide 10 by 2, b to the 5th. Multiplied by the radical of 14a. Now push these and unite these together. Negative 6 times 2, negative 12. A to the 1 times another a to the 1. Add those exponents, a squared. B to the 1 times b to the 5th, b to the 6th, multiplied by the radical of 14a, and he is done. Now, one thing about this before we move on in this little section, one more thing about this. When we think of simplifying, it would seem like that we should get an answer that would not be so extended looking, but that is not always going to be the case. It's simplified because our radicand now contains no perfect square factors other than the perfect square factor of 1. We're done. Let's quickly move to 7. And I think we're going to change the index. Got to be careful now. Let's get him ready. Assuming that he can be simplified, let's take our time and let's get it set up. Don't forget the 3. If you forget it, there's deductions. You got to remember the index. Now, let's pull 24 off and keep this in mind. Because the index is 3, when we prime factor 24, we are seeking the largest perfect cube factor that 24 has. So what are we going to have to see up here when we prime factor? 3 of a kind. 3 of a kind. 3 of a kind. 2. 2. 2. Now, folks, this time, only because the index has changed, I am going to use a little bit of exponent work. You don't have to, but I'm going to. Here's our 3 of a kind. I could multiply those 3 2's together, which would generate 8, and you are more than welcome to put an 8 right there. I'm going to choose not to. I'm going to write it as a power of 2. Inside the irrational, that little loner right there. Now, when we simplify this, you see that the exponent in the radicand is evenly divisible by the index. As long as he's divisible by the index, he represents, in this case, a perfect cube. Bring down the 2. If we divide 3 by 3, we have 1. We have 2 to the 1, or simply 2. And that's going to get multiplied by the cubed root of 3, and he is done. 2 more I want to do. Let's go to number 8. The cubed root, 192, x to the 11th. Get him ready. Put the index. Let's get 192 there. He's even. 2. I believe that will give us 9 times, I think 96. Do 2. He's still even. And I believe he'll give us 48. We can do 2 again. That'll get us 24. We can do 2 again. That'll get us 12. We can do 2 again. That would give us 6. And we can do 1 more 2, and that will get it down to 3. Your index is 3. We need 3 of a kind. We have 3 of a kind here. We have another 3 of a kind here. Now, folks, I want to slow this down. In this rational house, you could do one of 2 things, and I want to say this carefully. You could write your first 2 to the 3rd here. Put a time sign, and write your second 2 to the third right next to it. Or if you choose, you could total up all of the factors of 2 that you have, and you're still going to get an exponent that's going to represent a perfect cube, because you're going to have a 2 to the 6th, and the exponent of 6 is evenly divisible by 3. You can leave it this way. There's no problem. The leftover 3, let's come down. Start with this one. Bring down that 2. 3 divided by 3 is 1, so the cubed root of 2 cubed is 2. Put a times sign. Bring down this 2. 3 divided by 3 is 1. Times the cubed root of 3. Multiply 4 times the cubed root of 3, and that would be the simplified answer. Chris, and I've got one more. All right. Let's take care of that number 9. Change the index. You have to see the different types. Index of 4. 96. X to the 6th. Y to the 15th. Z to the 8th. I just realized something. I'll come back and get that back on number 8. I forgot something. It just dawned on me. Not perfect. Get this thing ready. Start with 96. Do it by 2. 48. Do it by 2. 24. Do it by 2. 12. Do it by 2. 6. Do it by 2. 3. The index is 4. We need 4 of a kind. We have 4 of a kind right here. Those are going to be leftovers. I could multiply them all together, but I'm not going to. I'm going to write it as a power of 2. 2 to the 4th. Inside the irrational, this leftover 2 times that 3. And now what I had forgotten on problem number 8, I'm not going to forget it on number 9. Let's go to the variables. X to the 6th. X to the 6th is not a perfect 4th because 6 is not evenly divisible by 4. But there are enough factors of 6 to generate an x to the 4th. You subtract, or you go down from 6 until you get to the first exponent of x that is a perfect 4th. X to the 5th isn't. X to the 4th is. Put an x to the 4th in the rational and just make sure. When you subtract that 4 from that 6, you'll be left with x to the 2nd. That goes in the irrational. Go to the y to the 15th. 15 is not evenly divisible by 4. We go down from 15 until we hit a number, the very first number, that is divisible by 4. No for 14. No for 13. Yes for 12. So we can pull out a y to the 12th, and 12 subtracted from 15 would leave us with a y cubed. Then go to the z to the 8th. 8 is evenly divisible by 4. Z to the 8th is a perfect 4th. Simplify. Bring down the 2. 4 divided by 4 is 1, so we have a 2. Bring down the x. 4 divided by 4 is 1, so we have an x to the 1st. Bring down the y. 12 divided by 4 is y cubed. Bring down the z. 8 divided by 4 is z squared, multiplied by the 4th root of 6x squared y cubed. And we would have that given answer right there. Now, if I can just quickly go back, I'll feel bad if I don't make it right. Back to number 8. That cubed root of 192x to the 11th. Just quickly get it ready. That 192 was 2 and 96. That was 2 and 48. That was 2 and 24. That was 2 and 12. That was 2 and 6. And that was 2 and 3. Here was one of those 3 of a kind, and there was the other one. Maybe a bit of a blessing in disguise, just so that you can see the other way. The first time around, I put a 2 cubed and another 2 cubed here. I'm just going to tally them all together, and we'll have a 2 to the 6th. And the leftover 3 goes in there. What I forgot was the x to the 11th. Apologize, but now we'll pick it up. 11 is not evenly divisible by 3. Go down from 11. No for 10. Yes for 9. X to the 9th would be the largest perfect cube factor of x to the 11th. 9 from 11 would leave us with an x squared in the irrational. Down. 6 divided by 3. 2 squared. Bring down the x. 9 divided by 3, x to the 3rd, multiplied by the cubed root of 3x squared. Yes, we would want you to change that 2 squared to 4, and we'll have 4x cubed times the cubed root of 3x squared, and that would be our answer. So you have seen quite a number of examples that cover rule number 3. Division will be next. Thank you. Okay, now we're going to put the product rule of radicals together in the sense that oftentimes you have to multiply radicals together first, and then you might have to simplify. So we're going to put both of those facets of the product rule of radicals together. Now here's that product rule. Sometimes we have to multiply first to get a single radical. And then when we get that single radical, that radical might be able to be simplified, as these 4 problems are going to show us what to do. So you'll notice the directions. It very clearly says multiply, then simplify. Folks, I'll be up front with you. On an exam, you might not see this kind of a direction. You just might see the word simplify. You might just see the word simplify on an assignment. But when you look at the given problem, like we're looking at number 1, if there are 2 radicals given to you with a multiplication sign in between, well, you want to multiply them first. And then once we multiply them, then we'll look at that single radical and see what we can do. So let's multiply. The radical of 3 times the radical of 15. 3 times 15, 45. Now we've gotten it down to the radical of 45. Now if that can't be simplified any further, then we would be done. But it can be simplified. So I'm going to get it ready. We're dealing with square root. If you look at 45 and you already see that the largest perfect square factor of 45 would be 9, put it in. But if you're not quite sure, you can be sure. By prime factoring, you can't do 2, but we can do 3. And it'll go 15 times. We can do 3 again, and it will give us 5. There's our 2 of a kind. 3 times 3 is 9. Put it in the rational. Put the leftover 5 in the irrational. And now let's simplify from there. And we'll have 3 root 5, and it is done. We had to multiply, then we had to simplify. Okay. Number 2. The radical 20x squared times the radical 2x. Now here's what I would suggest. When you look at this first radical expression, you might look at that number factor of 20 and see that it contains a perfect square factor of 4. And you very likely would also see that the x squared is a perfect square. You could simplify this first radical down to its full answer and then multiplied by that radical of 2x. I don't know if I would suggest that. I believe it's just as nice to multiply the two radicals together, even though 20 times 2 will generate somewhat of a bigger number. The numbers are never too big to work with, because you can always prime factor. So I'm going to multiply first. 20 times 2, 40. X to the second times x to the first. Now let's get it ready. 40, 2, 20, 2, 10, 2, 5, 2 of a kind. We don't have another 2 to join with him. So 2 times 2, or 4, will be the largest perfect square factor. 2 times 5, 10, goes in the irrational. X to the third. Within x to the third, there's an x to the second. Drop it down by 1, you'll have an x to the second. That's the largest perfect square factor of that x to the third, and that remaining factor of x in the irrational. Now, let's pull all of that out. We'll have a 2x multiplied by the radical of 10x, and we'd have our given answer. Doesn't matter how large the number is, we always have that. All right, let's increase the challenge by maybe just a bit. And let's go to 3. -6 root 50 multiplied by 2 times root 12. I'd multiply first. Multiply the factor of -6 times the factor 2. -12. Multiply by the radical of 50 times 12. You can just bring down that first 0, and now you can just multiply the 5 by the 12, and that'll give us 600. Bring down the -12. Now we're going to bust up 600. Let's give ourselves a little bit of room right here. By the way, some of you just might see this. I know there's going to be some. You look at 600, you might see 100 as the largest perfect square factor of 600. But not everybody's going to see that. They're just not. But we can do this. 2, 300. 2, 150. 2, 75. Can't do it by 2 anymore. Let's go to the 3. 7 plus 5 is 12. Yes. 3. 25. 5. 5. Let's look at 2 of a kind. There's 1. No, not enough. No, not enough. Yes, enough. Now, you can do this. That's 4. That's 25. 4 times 25 is 100. And you can put that whole kit and caboodle in the rational. If you want to put a 4, that little times sign, and put 25, you can. But I think this is reachable. 2 times 2 is 4. That's a perfect square. There's 25. That's a square. So their product will be a square. 4 times 25, 100. And now the leftovers. 2 times 3, 6 will go in the irrational. Bring down the negative 12 times the radical of 100, 10 times root 6. Negative 12 times 10, negative 120 root 6. Take it to the bank. It's done. I like this. I want you to like it as well. I think it's a nice thing to do. It gets us out of jams. It doesn't cause a migraine. Let's erase. And let's pick up this last one. The index now will change. Oftentimes it's square root, but you got to look at the index. Number 4. The cubed root of 32. X squared y times the cubed root 12x squared y. Let's multiply and get a single radical. Don't forget that 3. 32 times 12. It doesn't matter, folks, how big that is. 32 times 12, that'll give us 64, a placeholder, 32, 4, 8, 3. Let me just make sure that that's okay. 4, 8, 384. Now let's multiply the variable parts. X to the second times x to the second. Add those exponents. X to the fourth. Y to the 1 times y to the 1. Y to the 2. Now let's get them ready. That index in there. And let's go with that 384. Even 2. 1, 9, 2. We can do 2 again. That would be 9 times, it's 18, 1 left over, that's 96. We can do 2 again. That would go 48. We can do 2 again. That would be 24. We can do 2 again. That would be 12. We can do 2 again for 6. We can do 1 final 2, and that'll be 3. Now let's first of all honor the fact that the index is 3, so we need 3 of a kind. Well, there is 3 of a kind, and here is a second 3 of a kind. Those are our leftovers. I'm not going to look at each one of those separately. If that's a perfect cube, and that's a perfect cube, if we use the product rule of exponents and just put these all together, we'll have 2 to the 1, 2, 3, 4, 5, 6. We'll have a 2 to the 6th. And then in the irrational, we'll have 2 times 3 or 6. And now let's take care of the variables. Within x to the 4th, our index is 3. Within x to the 4th, there is an x to the 3rd. So x to the 3rd would go in the rational, and the leftover x will go in the irrational. X to the 3 times x to the 1 is x to the 4th. Y to the 2nd, there aren't enough. Our index is 3. Our power of y is less than that. We don't have enough factors of y to generate a perfect cube. So that entire y to the 2nd goes in the irrational. And now let's pull this out. Bring down that base of 2. Divide 6 by 3, which will be 2. Bring down the x. 3 divided by 3 is 1, so just x. Multiplied by the cubed root of 6xy squared. And now we'll just change that 2 to the 2nd to a 4. And I'm going to do that right here, folks, because I'm right down here at the bottom. That 2 to the 2nd will become a 4. And there it is. That would generate that answer. Now that takes care, I'll let you know right now, that's going to take care of part 1 of this 9.2 section. Part 2 will involve division. And when we do the division rule, there's going to be 2 parts to that. Dividing and simplifying as well. See you in a while.